In this module, we'll cover some more volcanic rock terminology, naming volcanic rocks, and a few of the physical and chemical properties of volcanic rocks. You've already completed an assignment that asked you to think about what different terms mean that apply to textures of volcanic rocks, including aphanitic and porphyritic. Aphanitic being a texture that is where the crystals are too small to see with your naked eye. And then porphyritic, where you have two different kinds of textures, a ground mass or the matrix of the rock having a very fine grained texture, so an aphanitic texture in the ground mass, and larger crystals within that ground mass that are called the phenocrysts. Now, those textures apply to products, volcanic products that result in crystallization from a lava flow, but there's also pyroclastic material, and those are pieces of volcanic materials, ash, gases, rock, and lava fragments that are erupted out of a volcano. And if they are lithified into a rock in any proportion, then they get a fragmental texture. And that only applies to pyroclastic rocks. That's a rock composed of that pyroclastic material. Or we can have a glassy texture, and that could be an obsidian or a pumice, which is just volcanic glass that is very frothy, so it has a lot of air bubbles in it. And we can also get vesicles or have a vesicular texture where there are holes or pore spaces or other cavities that form as gases are escaping from the volcanic rock from a lava and end up trapped and preserved as holes later on. I showed you this image before to compare side by side the same chemistry but different textures in plutonic and volcanic rocks. You see here again on the left, the plutonic rocks are phaneritic, have a phaneritic texture because you can see the individual crystals. And the volcanic rocks, while there may be a few crystals that are large enough to see in those phenocrysts, generally they have an aphanitic ground mass, and you can't see what the minerals are with your naked eye. Or we can have a volcanic texture, a glassy texture like this obsidian, that's not crystalline at all, that is glass. You've used an IUGS diagram like this to name plutonic rocks, but given the fact that volcanic rocks have very fine-grained textures, it's going to be very difficult, if not impossible, to use this diagram to name volcanic rocks, because if the crystals are too small to see with your naked eye, and maybe even with the microscopes, you won't be able to estimate how much quartz or K-spar or plagioclase is in the rock. So that makes the volcanic version of this IUGS diagram not terribly useful. Instead, to truly name a volcanic rock, what you need is the chemistry of the rock. And so that would be if you could crush the rock into a fine powder and then send it to a facility that where they can collect XRF or X-ray fractionation information about the chemistry, then you can plot the rock here and name it that way. And that requires, this is comparing silica on the x-axis with the alkalis, so sodium plus potassium on the y-axis. But what does that leave you with in this class? Because we don't have an XRF machine and we're not going to get chemistries for the rocks that you're going to look at in hand sample and thin section. So let's just have an example. Here's an example of an andesite. I'm telling you it's an andesite, but how would you know it's an andesite? There's this light colored ground mass with some phenocrysts that look like they're all hornblends or pyroxenes sitting in that fine-grained ground mass. How are you going to name it? It's very light colored, so it has the color index is low. It's a small percentage of dark minerals. It's a light colored rock. How in the world could you go about deciding whether this is a rhyolite or an andesite or some other volcanic rock name that might apply to a lighter colored rock? I think you would immediately guess that this isn't a basalt because it's not a very dark rock or a black rock. So what are you going to do? You'll have thin sections too, and the thin sections will be helpful in identifying the phenocrysts if you can't identify them from the hand sample. In this example, you see, what looks like maybe hornblende or pyroxene phenocrysts, and then you look in the thin section and you see minerals with a second order birefringence. Here's first order birefringence. Maybe those are pyroxenes. You see something that looks like plagioclase. But what about all of this stuff? What is in there? Very tiny crystals we call microlites that are almost impossible to identify. Maybe you could look at this one here and say, well, it's elongate, it has first order birefringence, it's probably a feldspar of some kind, maybe a plagioclase like this other one over here. So you're kind of stuck. You're stuck. Some of the crystals are just too fine-grained to identify. What are you going to do? It boils down to this. You're going to use a combination of the color index of the rock, the composition of the phenocryst, what minerals can you identify, and the birefringence of the microlites to help name the rock. So let's say in this image, you don't have the information from, you don't have this information from the large phenocrysts. Maybe you don't even have the large plagioclases. You certainly don't see that. But you can see first order interference colors there, and it's an elongate crystal. Probably it's a feldspar. If you were to see a smaller version of this pyroxene, that's too large, that's very easy to see, but you might be able to see very small microlites that have a second order birefringence. That's going to help you to identify the rock. And it's somewhat of a guessing game, but it's an informed guess. All of those things together, the birefringence of those microlites, the composition of the phenocrysts, and the color index all go into trying to assess, whether you have a mafic, ultramafic, or felsic rock. And how you're going to use this is basically what Bowen's reaction series tells you. So if you are looking at a rock that has an uncertain color index, let's say it's just kind of gray, and it's not light, it's not terribly dark, but what you can see are olivine and pyroxene phenocrysts. And maybe you can use the Michel-Levy method to establish the calcium content of the plagioclase, let's say the larger plagioclase microlites, and you can see that it's calcium rich. Well, that is really helpful because then you're looking at a mafic or ultramafic rock. Now, there are no modern ultramafic volcanic rocks. There are ancient ultramafic volcanic rocks, but there are no modern ones. So, and those are called komatiites. Komatiites. Oh, oops. Let's try it here. Komatiites. It's from the Komati River in South Africa. So they're ancient ones, but I don't have any komatiites in this lab, and so you're going to focus on mafic, intermediate, and felsic volcanic rocks. All right, so if this works the same for any of the rocks. So you've got some, let's say you can identify amphibole and plagioclases of some unknown calcium content. Well, you're kind of in this area, somewhere between mafic. It could be even felsic. It's probably intermediate in composition. But I hope you get where I'm going. If you see case bars, quartz, phenocryst, particularly you have quartz phenocryst, you're probably going to have a felsic rock or a rhyolite. So this is what you're going to use to try to name these volcanic rocks. Now, a little bit about the properties of the different magmas. And I'm including this because what we've been talking about is basically the composition of the rocks and how it affects the color index and also the composition of the phenocryst. The properties of these volcanic rocks relates in large part to the silica content, and that's also part of the chemical differences between mafic, intermediate, and felsic volcanic rocks. You'll see that rhyolite has a very high percentage of silica, somewhere between 70-75%, and basalt has a significantly lower amount of silica, around 50%. And even though that's maybe 20-25% difference, that has a big effect on the properties of the resulting lavas. So, for instance, the silica content as well as the temperature, you'll notice that the temperature of mafic volcanic rocks is significantly higher than the felsic volcanic rocks. And the low silica plus the higher temperatures in, let's say, a basaltic lava leads to a thin, runny lava. This is not very viscous. It's a low viscosity lava. Viscosity is a term that describes resistance to flow. And so basalt is, with its low viscosity, is going to be runny, spread out over large areas, and form things like shield volcanoes, like the volcanoes of Hawaii. Whereas rhyolite, with its high percentage of silica, the lower temperatures, it's still pretty hot. It's molten rock, but it's significantly lower than the temperatures of the basalts. That leads to sticky, very viscous lava that also affects the landforms that result. So those lavas don't flow very far and form things more like lava domes. And I'll show you in a moment. Now, you've probably seen in person or in images basalt lavas that look like this. They're ropey. They look like, it looks like solidified liquid. In this case, these are pahoehoe lavas. And these are the less viscous kind of basalts. And part of what's affecting the viscosity is not just the temperature and the silica, but also how much gas is in and how many phenocrysts are in the lavas. The phenocrysts are forming before the lavas erupted, and those phenocrysts are crystallizing early on while the magma is still in the magma chamber. And then when it erupts, it's bringing all these phenocrysts along. So the percentage of the phenocrysts in a lava, as well as how much gas, is having a big effect on the viscosity. Compare that to an lava that has this jagged surface. That's because That's because it has a higher viscosity than the poehoi because of the amount of gas that's in the lava as well as phenocryst. Now that's very different from a lava dome, and this is a lava dome in the crater of Mount St. Helens. And here's an old one, here's a new one that's steaming and fresh. They form these little plug domes, they're called also, of very viscous, it's crystallized viscous felsic lavas, and so rhyolites. So very different landforms for, depending on what kind, the composition of the magma for that volcano. Now you've also seen obsidian before. Pumice is also glass. It's just a frothy glass. And I want to show you this again because look at the color of the obsidian. That color, that black color of the glass, could be misleading to you. It's actually rhyolite in composition. Even though there aren't, it's not crystalline, you can still do the chemistry the same way you might for a product of a lava flow like a rhyolite and see that it's rhyolitic. But it has this dark color because of the glassy texture. Same thing with the pumice, it's rhyolitic. So beware of the color index. All right, what you learned in this module is that volcanic rocks are difficult to name because of their fine-grained nature, that the color index of the volcanic rocks can be misleading. So you're going to use the color index as well as the type of the phenocryst that you can identify and the birefringence of the microlites to help name a volcanic rock. Now I'd like you to apply what you learned here to volcanic rocks that you're going to see in the lab.